And thank you again for coming, for these opportunities. I'll try to continue our work. And so, remember, yesterday we finished more or less defining this set. As essentially the set of resource functions with zero value. So now I'm trying to put more or less in this setting to apply some multiplication theories. So we denote by UR a subset in this space. Which is neighborhood of function 0 such that around here we have a solution to the Richter problem. What is it? I mean, in other words, it means that this is a smooth domain, a compact domain. You know, I mean, since it's an embedded hypersurface, if phi is small, this perturbation is still a compact smooth domain. Okay, so what we are actually avoiding is something like that. You know, you could have some problems, but we always have a good set if you take small functions. Okay, that's it. So, and then, so in this case, you have a solution, and then we take this solution. Remember, we have two maps. Have this set, this cylinder, have this graph perturbation, and we have our domain. And here we have a map, capital phi, and here C, which is depending on R and Y. Okay, and then we denote by UR phi. So in this case, we have a solution. We will then take the pullback. So it is. Is it? Yeah. Okay, so recall that. So that is. It means that recall that we pull back the map here. It is that. So you solve this problem. Okay. Well, we also need.
Can you recall DR
This guy?
Yeah.
Okay. Yes, sure. You have your cylinder. Okay, this is just the R example is this product. When you put a 5, you can describe it explicitly, but it's just a graph by. So this is
And omega?
Omega is the image of this guy. So, okay, let me go 1 second.
The base is G over H, the base,
Yes.
and phi is defined on G over H. And it's very
Exactly.
close to 0, so you fulfill the property of having hypersurface.
Again, just a minute. The point is, under our hypothesis, there's a difference between these guys and the whole manifold. The non-principal words. Okay, so this is more or less a trivialization when you remove this set. And so this is a cylinder. As Joaquin said, the base is this manifold. So this is a, let's say, this is R. And so if you have a function phi defined on G over H, if it is small, this set D R plus phi is the graph, just the graph over this set. And actually is the domain below the graph. Yes.
I think it's important. That the definition of the U R
You are 3 or 5 is
Maybe wrong.
first row
is U
first
applied
write
that.
U and then write the inverse.
Of course, sorry. Thank you.
It's not
Right.
not important.
I like to write the pullback, but
Yeah, sure.
yes. So this function defines the corresponding points. Thank you. Right.
Es la phi primero, después la C.
And then you remove.
Okay, let me just 1 second. So
Empieza desde U.
aquí está U. So here's U, okay?
No.
U is there.
Yes, right. This U, and this guy is.
Now
Yeah, perfect. Then you don't have to write.
Nice.
Okay, perfect.
So it's recording. You can just
Well, geometries, we
Yeah.
the
Right. Maybe you can solve it just with a picture.
Yeah.
Thank you. Okay.
We will edit the video. No problem.
Thank you. And so, okay. We do the same with the symmetric solution, and we denote it by so ZR 0, 1. This guy is just 1. Okay. So the pullback of this. Anyway. Yes, so we define now this new domain, which is the union of R times UR as R belongs to this set. So it's a subset of Okay, so this is an open set here. It is product by a line and a blank space. So now we define. Okay, we're ready to define the function f. We are looking for. So this is look minus r. So essentially the solution to the derivative problem. Okay, so if you yes, so this the image is defined in this manifold. So right like that. Next, this is this derivative less. Well, in this, so this is the pullback. What you want is, in this case, 1 over r z, which corresponds to y prime at r. Okay.
What is the meaning of the eta or n in the denominator?
This is the normal unit vector
To the graph over G over
to
H?
actually this
defined by
guy
R
is the
and-
pullback to D1. Okay, so the point is we are trying to do the calculus, the computation in this fixed domain. That's the point. Okay, so this guy could be the average also of this function. It's not so we have phi over here, of course, and yeah. So the point is if have a zero of this function of this operator, this function, then the corresponding domain plus supports well, solution to the Serrin problem. Well, actually, I should write another way. So once you find a solution to this equation, the corresponding domain, the derivative solution, has constant normal derivative along the bottom. This is very okay. And so this choice here, I mean, this is just a constant with respect to phi, but of course, you can see that in this case, okay, you have at the end the domain omega r, where you know this corresponds to the Hagar solution. So this is so we need this condition to try to apply this equation. That's the second. All right. Before continuing, let me make here an important remark. So, like I mentioned that Renato and John considering the same set to find CMC hypersurface in cohomogeneity 1 manifolds, bifurcating from essentially this family, the boundary of omega R. Okay. So this is a paper of 16, and I write this. This resistance of CMC of Delaney type. This is the type of CMC at the surface. From this family in this setting, I mean, homogeneous. And so this paper is very important for us because this is exactly the setting we are working now for the same family actually.
Can you remind what is sigma?
Sigma R, sorry, is, remember, omega R. So the principal words of the action. Right. So remember they have constant mean curvature, and of course depend on R, and so they apply the same method to perturb, and at the end, and we hope have the same. The perturbation solution also have some symmetry, and then that's why they call Delaney type hypersurface. All right. So the same set. But have some hypotheses.
And the functional is the functional f here.
Of course, it's different.
Curvature,
right?
Minus the curvature of this cylinder.
Minus. Let me remember. All right. Yes. Minus the curvature of the symmetric one.
Okay.
That's the point. That's interesting. The solutions in both cases. So the value of the derivative, in our case, for example, the value of the derivative is the same as of the radial solution. That's what I'm saying at the end. And here's the same. Okay. Well, I also recommend a paper.
It is not the same because it is minus its mean. So
Sorry.
Can be different, no?
No. Look, if so, there's no 5 here, right? And this is exactly minus this guy. Okay, is it right? Yes. Okay, and this minus is just because the orientation. So, okay.
So it is not the mean of the average of the sum.
It's the same.
It's the same, but so it depends on the deformation. If it is the average of the deformation, depends on the deformation.
Right. I'm not sure. I think it's the same. But we found a solution to this problem. Should be the same. You agree? Or no?
Yeah, but
Because
in one case,
constant is unique.
No, I mean, maybe there are rescaling that you can do.
Not for that equation.
Yeah, right.
For the Serrin equation.
Yeah, right.
They're not scaling variables. So actually, remember the constant. This guy is precisely minus. Depends only on the set, right? Okay, anyway. Okay. What I want to say now. Yeah. So let me just give us a definition, maybe you know, of what is a bifurcation instant. So we say that that's what we are looking for, is a bifurcation instance. If you find a sequence conversion to this number for which that are non-zero, non-trivial solution K, say, to the equation. So this is the usual definition of bifurcation point. So that's interesting. It means that, so for that point, of course, we have the symmetric solution, but we also have a sequence of points converging to the point with other solutions, not only one, but exactly the notion of what is bifurcation, at least a sequence. Hopefully, a curve. Okay. Yes. So, and then, of course, I mentioned yesterday that everything starts studying the linearization of this function f. Okay, so let's define that R. So this is you take R, and then this is defined here. This is what we this derivative with respect to phi. Okay, that's phi 0 applied to omega. And then the point is we look for points such that the kernel of this operator, right? And so I will call key proposition in paper. So it's a long computation, right? Is that this operator, the linearization, is given by where, surprise, so this operator is defined here, is the stack log operator, is the Dirichlet to Neumann operator on this let's say principal words sigma r. Okay. this is surprising for us, more or less surprising. Of course, it's very related. The first way you can see this is when you consider the equation, the derivative. When you imagine you can just compute the derivative of that equation, the constant disappears. So you have in the space of the derivative have only the Laplacian equation, harmonic functions, but on the boundary we have the condition of normal to derision to normal. So it means that if omega is a function defined on sigma r, right? The boundary of the domain. This guy here is, remember, it's isometric to this manifold with the metric GR, homogeneous metric. So you take a function here, and so SR of this function is the derivative of omega, of the harmonic extension of omega to the bound, right? So the deletion, the stack law, the usual stack law operator. Let's say that, well, the proof has a trick, of course, and the trick is in the paper, many papers. Okay, so but that's interesting because so it's not easy to compute. You know, we are applying the derivative with respect to phi. But so you need some auxiliary function, and so you take the same idea, for example, paper West and also Fall, Milan, West, and the same idea works in this general setting. Okay, so I prepared some 5 pages, but I will skip the proof. All right. Okay. So we denote the stack law of eigenvalues by so let's look sigma 1, and this guy is bigger than 0. The stack law of eigenvalues. Of course, this guy is me. Are the eigenvalues of our theory. Okay. Okay. Just mention here in this point. Remember, we are considered functions with 0 mean, and so this take off the constant function here. So 0, which always eigenvalue for the stack law operator, is not anymore in our space. Okay, so the first eigenvalue is strictly positive always, but he has some multiplicity, of course. Okay, that is the set. Again, for example, in the paper of Morabito last year, Fall, they have the same computation, but they don't point out that that was the stack law operator. It's over there, the definition, but there is no the name. Okay, somehow it helps us, and let me make an example. Remember what happens in open space. All right, so omega is the ball produce R. So we call that this solution T. So this is the symmetric solution, okay? So the stack law eigenvalues of the ball, the sphere, as you wish, they are okay, and so as I said, k is given 1, and then you can put in this formula and get this guy they are all negative. And only the first one is 0, okay? It corresponds to the first eigenvalue of the Steklov problem in the ball, and they are generated by the coordinate functions, which corresponds to infinitesimal translations in the Euclidean space. Okay, so translations preserves the volume. They are perturbations, but in this so the solution is stable. And since the other they are strictly positive, so have no solutions, have no the only functions on the kernels are generated by translations. Any other perturbation have a strictly positive eigenvalue, which means that we have no solution to the problem. I mean, it is like a proof of Serrin in the case of a small perturbation. Okay. Okay. I have a remark to the end of the talk, but let me make right now. We are trying to have the same result. I mean, try to prove infinitesimal rigidity of the symmetric domains for the Serrin problem in non-compact symmetric rank 1 manifolds. Okay, like the hypothesis. But well, in the hypothesis space, you have the theorem I mentioned yesterday, but you don't have a Serrin theorem, for example, in the complex hypothesis space, for example. Okay, or in the quaternionic hypothesis space. And essentially, we tried to do the same computation because we have the solution, we know the solution is explicit, but we don't know what are the Steklov eigenvalues in this space. If you know, please tell me. Okay, do you understand? So if I like to do the same argument in other space, essentially I need to know what are the eigenvalues of the Steklov problem, and we don't know. Yes. Exercise for the students. I really it's an exercise. Have a test. Okay, and now, okay. All right. Let me. So our approach now depends a lot of understanding the Steklov eigenvalues. All right, and it's very important. Analysis of symmetry. So consider, look at sigma r they are the stack law of eigenvalues for the symmetric domain, omega r, right? Not two. So should be easy. So consider the problem. Let's go here and okay. So this is the stack law eigenvalue problem. And so he called that the metric here. I mean, is a product. Okay, you can use it to prove that this Laplacian here is given by this guy. This is the met on t times g over h. Okay, so we're using separation of variables. We can consider v as function, and where this is eigen. So this is a function defined here, and we take it as a eigen function for the Laplacian operator. Okay, so that this guy, and again, I got this idea from the paper formula and West in the sphere. They did that. Okay. Okay. And so you put this function in the equation using the Laplacian like that, and you find, you can simplify the x, and then you see that. So if V is a solution to this problem, then T is a solution to this ODE. Okay, yes. So this is a singularity. And what the conditions do we have at 0. So in this case, if you have a solution, okay, so if you have a solution to this problem, then you plug the solution here, you can cut off the function x, and then you get this. Okay, and recall that we have the precise behavior of the main curvature. Okay, but we don't have for the first eigenvalue of the Laplacian. Okay,
Repeat
so
that.
sorry.
Repeat that, please.
So we have this equation, okay, and this is a singular ODE because remember, this guy in general blows up. In general, the only they blows up. Sorry.
At zero.
at zero, right? So I mentioned the paper of Mazel Pacar. So it is, so this is
And one over
minus d, that's interesting. Okay. Let's go to zero. And this blows up except in one case when the non-principal of sigma zero is minimal. Okay, when d equals to n minus one, which is exactly the same of the sphere. When you are in the sphere, so this is minimal, and this the mean curvature of the principal converges to zero. So d is n minus one, so this is zero. Okay. But when this orbit has less dimension, the mean curvature blows up. Okay, so this is similar here. And in general,
Lambda also goes up.
sometimes, right? Yes, mostly case, that's the point. And then, well, as I said, we know the behavior, and we using the Frobenius method, we can prove that if this guy remains at least bounded as t goes to zero, then let me call two. I mean, let's see, one for the first equation, maybe. But at least here is two. Okay. Then two has a solution. And is it here? In this case, so this is smooth at zero, and this goes to zero.
Just one question. That problem, the spectral one, you can consider it for infinitely many values of sigma. Sigma is the spectral eigenvalue.
If you have a solution, yes.
Right? Now, there, lambda
Right.
is for the first of any eigenvalue of the Laplacian.
Right.
My question is sigma, the sigma that you have given here, the formula,
Right.
is for sigma 1?
No.
Is that lambda 1? Or is for any? Is for
Okay,
any?
yes. Once you have a solution to this problem,
Oh.
once you have a eigenfunction, we plug it here. Okay. And so when you plug this, this equation
Is satisfied for that formula.
right. So it holds once you
Okay,
have.
then let me pose the question in another form.
Okay.
Is increasing in the sense that if I have lambda 1, lambda 2.
Okay.
Right?
Right.
And then I have capital T1, capital T2.
Okay.
The sigmas are ordered the same way as
Right.
the lambda.
Yes. That's amazing. It is a lemma precisely in this way in a recent paper of Castillon Rufin. Maybe 2 years ago. They studied, that's nice paper. They studied the stack log eigenvalues in symmetric spaces, cross, actually. But they found a kind of Weinstock theorem. Okay, so they don't have the explicit eigenvalues as we need, but they have a study of the eigenvalues of stack log problems. And so this is a special case of a cohomogeneity one manifold, and they found the same ODE, the same problem, and they proved this a lemma, explicit lemma. Yes, Castillon Rufin. I don't put the number of the lemma, but right. So let's say lambda. But you know, I mean, the proof is simple. You can use a cut comparison method. I will mention 1 second. And let me put the Philippe Castillon and Rahim. The paper is a lot of important results. Just a lemma in the paper. If I mean lambda 1 doesn't matter which one. So I put I and J if you wish. Then right. The corresponding guy, okay. One say also respect the same. All right, that's interesting. I mean, there are a lot of interesting things in these guys. Okay. Right, it's exactly in this sequence. Thank you. Okay. Yes. All right. Okay. So, I mean, let me say, it's very important for us, this behavior here, but it's not the case in general. All right. As you can see in the first example, all the eigenvalues of the stack log goes up at 0, right? And put a remark here. If the dimension of sigma 0 is 0, okay? So the domains omega r, they are actually Jodesky balls in the cohomogeneity manifolds. As r goes to 0, it becomes very close to the Euclidean space, and then all eigenvalue of the Laplacian of the spheres blows up. They are not bounded. Let me write like that. Okay. So the eigenvalue of the sphere, actually the Jodesky sphere, blows up. So, and you have no control on sigma. And so this leads us to our first condition, our first hypothesis in our filtering theorem is that we need at least dimension 1 in the singular object sigma 0, right? And we hope to prove the opposite side. So always, if it's the case, it would be nice to prove you have a local rigidity. You don't, yeah, I mean, at least close to 0. Maybe.
The fact that the mean curvature is Dakar paper, n minus 1 minus d,
right,
divided by r.
Right.
So
D 0, in this case D.
D 0 in that case, yes, no, but what I say is that in order I don't know.
Okay,
I would say that D has to be n minus 1. You have to, the other D has to be 100%.
So let's see that. No, almost that. Almost that. Yes, sorry. I take more than 1 hour, sorry. Okay.
It's okay.
So, thank you. All right. We need let me make a new example. Let's try. Yeah, we need a new hypothesis in a few seconds. Before that, let me mention the example of the three sphere S3. Okay. So domains this guy. And well, at least the eigenvalues of the Laplacian problem equation is simple here. I mean, the spectrum, okay, of the Laplacian of this guy, I will call sigma. Well, there are two indexes, okay. Depends on R. It is k squared cos plus RL sine. All right.
Square.
Square. Thank you. Okay. And what happens here? So this is that's very interesting example anyway. So you have two domains, you know, but we always choose one. In our case, we are choosing r goes to 0. That's the same when r goes to pi over 2. But anyway, so what happens? This guy blows up. Okay. As r goes to 0 if l is non-zero. But they converge. It's 0 here, okay? If L is 0, this is going to k squared, okay? And more or less, under some suitable hypothesis, this is the general case. Okay, so you get.
Now I understand. That's what I said.
Some eigenvalues converge,
very good.
and that's nice for us. More or less, it leaves implies essentially bifurcation. And you have another, maybe not. In the papers, what is the geometric mean in the papers? For example, if you assume essentially, so if you restrict your perturbations for even functions, for example, you have only this case. This is the geometric. How can you use geometry to lead with this problem? All right. So yes, in my notes here, I will skip this, but I already mentioned the solution. I have a explicit solution. So how can I say? I will draw just a picture, okay? We can prove this is minus 1/2, and you can see that the corresponding eigenvalues to the linear head operator, they converge to minus 1/2. They looks like that. Okay. But the other ones behavior more or less like that. Okay, this is the case of this family. In particular, we can perform the bifurcation at these points. But anyway, in my notes, I state the theorem in this case, which is nil. But let's go to the general case. Okay. All right. And this behavior can be C or can be, can I say, this is the case when you have a adapted method. I will explain more or less. And it is also a condition in the paper of Betriol and Pichon. I mean, the condition of a method to be adapted is quite tricky, you know, but essentially says that you can guarantee that some eigenvalues of the Laplacian converge to a finite set for the spectrum of the sigma zero. Essentially is that. Okay. So we assume the map G is adapted near sigma zero. Okay, so I will skip the precise definition, but in this case, the homogeneous perturbation fibers sigma t sigma zero is a Riemannian manifold, sorry, Riemannian submersion up to his scale. Attention, depending on for each t. Okay, so this is exactly the case of the torus. Okay, so you have a product S1 of radius cos r times S1 sine r, and you have a projection in one factor. And when you make a high scale, this is a isometry. Okay, so there's a more general concept in this case. And I mean, this is defined in the paper of Betriol Pichon, and they prove that under this condition, I guess square, this function goes to 1 as it goes to 0, and the spectrum of this guy is a subset of the spectrum of this guy. So when the sum eigenvalues converge to this, so this is actually the case. That's the case. So the big case. All right. So it's a technical hypothesis. Will be in the theorem in a minute. A while actually. I'm almost done. So I can state like a proposition. Some guys converse. That's what we need, right? Because look, I mean, this is exactly as in the example. You have a copy of the spectrum in the whole manifold. When you take the parameter goes to 0, so the idea is the following. Look, imagine you have R here, and you have a manifold. So this is sigma t, say. The spectrum of the Laplacian goes to plus infinity, all right? So essentially, under this condition, they are saying that some eigenvalues here converge to some eigenvalues, but maybe on others goes to plus infinity. That's what happened in this case, okay? Actually, let me say another way. That is 6 seconds in G inverse to maybe another one. That's it. And well, we still, under this condition, we still have a lot of examples of cohomogeneity one manifolds with this condition. All right. Okay. For example, the sphere, for example. Okay. Okay. So, look, we know that in any case, the eigenvalues of the stack log operator goes to infinity. All right, it's a sequence going to plus infinity, right? So this is the same for me k. Okay. So we have this. We don't know what the sign. Okay. And we fix R. We fix R. It's a sequence. All right. Going to plus infinity. And
What is the meaning of mu?
Me k. This is it was there. Me k is the eigenvalue of L R me. All right. And we found that it is. Good. That's a good question. I mean, if you're looking just for k, there's a small detail here. This guy is negative. Remember, it was an exercise yesterday. So the solution, the symmetric solution looks like that. So, but you have a minus. So this guy is grows to plus infinity. So the same for the eigenvalues of L R. So that's this. And K. This is one observation. The second one. I mean, I put here the. Yeah. Let me write. I don't know. Sigma k prime of t t sometimes I use t, another time I use r, sorry. Okay, so the eigenvalues of the stack log problem they are related, satisfy this Riccati equation, okay, and mi k also, all right. Sorry. So it follows directly from that equation and that. Okay.
So why is a solution to that equation?
Sorry.
Why is a solution to that
No,
equation?
y is the symmetric solution when you are in omega r. The solution depends only on the distance to sigma 0. This is, I mean, I mentioned it yesterday. Is this solution the symmetric case? The solution depends only on the distance.
It's like this.
Right.
In the case, in example.
Exactly. In the case of the ball, it is this function. Okay. All right. Okay. Now we start to. So I have only 2 papers, okay? Okay. Right. So, as usual, I will not buy this guy here. The eigenspace. Okay. And this guy. In the space of negative element. So it goes on R. And the index is mentioned of this space. Okay, but what happens here? We may have some problems. So, I want to use a powerful theorem in a minute. And the idea is to analyze the points where we have a change of the index. They are the candidates for bifurcation instant, okay? And that is a very interesting phenomenon. What happens? So, if I don't mention here, but if the eigenvalue lambda k converges, the corresponding stack level eigenvalues goes to 0. It's here, this claim, okay? And in this case, we can prove that mention here. In this case, this guy, the corresponding one goes to this guy, which is negative. Okay, so when you have lambda k conversion, sigma k goes to 0, mi k goes to a negative number. So we have something like that. Maybe one of them, another one I don't know. Okay, I have another one very nice, but the others, so they converge to the same point, and there is a sequence. Okay, something like that. But we also have some eigenvalues like that, going to plus infinity. And what may happen is, we don't believe in that, but may happen is, so this is a zero, okay? This is a zero for the eigenvalue, so at this point, maybe one of those eigenvalues that goes up here maybe intersect right here. So in this case, okay, what we have? The index becomes, could be constant, may not change. Let me show you, Jose. So this is the point, and you look in the neighborhood here, small neighborhood. Okay. Assume that, for simplicity, assume that all the other eigenvalues stay from here. So don't, indeed, at this point, this guy, all these guys, yellow ones, don't, they are both, right? Then remember, they are in a sequence, they are, so, I mean, let's say this is the 1, 2, 3. So after that, all these yellows don't contribute to the index, at least here. All right. But you may have the red ones. So you should have others like that, maybe below. But after that, the other ones will become above. All right. So what happens in this case? The index is the same. For example, in this case, the index is okay. All the eigenvalues has some multiplicity, but doesn't matter here.
So can you explain that again?
You can see, right? I mean, this is the index which should be. I mean, 1, 2, 3.
Okay. Now I see.
And you can see, but here, this guy, you have another 3. 1, 2, 3. That's interesting, isn't it?
Sí, en la parte negativa del plano, ¿vale? Aquí, a la parte negativa
Hay tres amarillos.
tres amarillos.
Y el otro
índice
dos amarillos
tres.
y
Dos
uno
amarillos.
rojo, índice 3. Lo van a cambiar el índice. Pero, sin embargo, el índice se ha mantenido 3 viniendo un valor propio positivo. A construir el índice.
So how can we solve it? I mean,
Yes.
how can Betjon solve it? Because it's essentially the same problem. Okay. Okay, I guess. So. All right. Time to finish. Right? Okay. So, following Betjon and John, we assume that H is a normal subgroup of K, or K is a normal subgroup of G. That's in the case. So G, this nice G, will be the quotient, okay? Sorry. G, which will be K over H, or G over K, right? Is a group. Remember? Algebra 1. And this group acts in the principal works sigma t. All right? That, in fact, this group acts on sigma t. Remember, this is sigma t is diffeomorphic to G over H. Okay. And its orbits. So I mean, this group acting here has some orbits. The orbits are of pi. Okay, so sorry. Of pi? Yes, yes. I guess. Oh no, the fibers of sorry. It's not pi, but the this projection here. G. Right. Yes. Sorry. Pi. Right. This. Right. And that so should be interesting if you can imagine the groups like if for example we call that H is a subgroup of K, which is a group of G, and you can imagine this guy like H times something, and this guy H something something. No, the simple case, and you can see this. All right, so to finish, sorry, I will use a powerful theorem to conclude, and that's the point where I'm actually studying right now. But my co-author is very confident. I believe him. Because actually the same case as the paper of Renato and Paulo. So under this condition, we can consider the subspace. For simplicity, I will call xg, right? Which is a subspace here of the subspace of functions which are lifting of functions on sigma 0. In the paper of Formula and West, they call this axisymmetric functions. And so when we are restricted to this subspace, all the eigenvalues goes to 0. Okay, so we don't have any more the red ones. Decays that come from some lambda k that converge. So, and now I will use a powerful theory. Please don't ask me too many details, but I'm trying just to put in the conditions. So, amplification, given by that's y'all, John, channel. Which is a generalization of another theorem by Muller-Weissman, 1990. Okay, we can do our theory. This sequence of multiplication instance. The same. Moreover, that's a nice point. The solutions, okay, the solution means the domains are G, that G invariant. Because we found we did all the perturbations in this class. And I'd like to stop here. Thank you.
Thank you.
I have a question about the algebraic meaning of that. I understand, of course, the algebraic meaning, but what is the connection between that part of acting on sigma t, no?
Right, I mean,
And the fact that you have bounded lambdas.
well, the point is, under this algebraic condition, the quotient is a group that you can easily check that this group acts in the octaves. Okay, that's the point. So under this and that's not true in general, unfortunately. For example, if you are in a high dimension sphere and you consider the group OK times of O n minus k minus 1, so we have a sphere of high dimensions, and so it's not, for example, a abelian group, and we have no this condition in this case, for example. So yeah. So the point is, under this condition, the quotient is a group that acts in the octaves. And then we can restrict everything to this kind of special functions, actually. And again, that's the way we can see in the papers in general, because when the Roberto follow in order to solve the problem, they always found some symmetries. What they are doing is actually restricting the space, the total space, to some space with symmetries. We understand that is the case. And exactly the same hypothesis as in the paper of Renato and Paulo.
Thank you.
Gracias. Yeah.
Perdón. Sorry. The result by Paul is a consequence, immediately consequence of this.
Right.
It's a coupler.
Right. Exactly.
You have exactly that.
Exactly.
Right. And also the result in the cylinder and the result in sphere, both are there.
Right.
Right. And if you want to generalize them, there are two generalizations that you can do. One is with the same equation, but for the relative problem. The relative problem is the same as, for example, free boundary surfaces. Right? It means you have an ambient manifold that you cannot touch, and your domains touch the manifold. Okay, so you have a mixed, not directly problem initially, because the natural condition is that the normal derivative is zero in the boundary of the manifold. And so you have the relative Serrin problem. That is the exactly analogous of the free boundary surface. Right. Can you do this generalization, this framework to test this argument to that framework?
Right. By the way, yeah, I mean, I don't know exactly, but there's some chance. However, you need to study the corresponding problem for the eigenvalues. For the Laplacian on actually that was studied by Zaremba. Do you know Zaremba problem? Is precisely this problem for the first eigenvalue when you have a domain with and you have a partition on the boundary, and then we have a, for example, Dirichlet at one part and the Neumann in the other one. And I mean, I don't know, I think there's a lot of job to do, you know, to have some kind of this problem. But I know your paper, recent paper with Filomena,
Exactly.
in the case of a cone, that's the case. That's interesting.
It's a cylinder, in fact.
Cylinder.
Yes.
Okay, right. Okay. Sorry. Yeah,
Because
maybe.
in the cone we didn't arrive through.
Okay.
In fact, we want to do in the cone,
All right.
but finally we were not able.
I see.
So in fact, there are difficulties from the ambient main. So I mean, here there are more.
Maybe, yeah. But yes, to the case with mixed boundary conditions, you know, I mean, we use a lot of classical things. Essentially, you know, our boundaries, they are closed hypersurface, and we use all this geometry, the eigenvalues. For the mixed problem, I think we need to, I mean, fill a lot of flags.
So you have a homogeneity one manifold in another manifold.
Yeah, see, I see, right, like the cylinder in the clean space.
And the last question is if you want to do this for other equations.
That's my dream, yeah. You know, I mean, yeah, it should be very interesting, especially the external domains, right? Even, but I talked with Roberto, there is a conjecture of Habassuan. He claims that in S2, the only external domains, they actually have, he said two conjectures, one for Schiffer, which we solved. The other one is for extremal domains. The extremal domains in S2 are only disks and cylinders. So if you can apply, I mean, we can try to do it in spheres, but in general, if you apply this technique to homogeneity manifolds to the Laplacian equation, in particular, hopefully you have a example. Yeah, I mean, that's the project. I have a lot of things to do to learn.
Yeah. Okay. Thank you, Marcus.
Yeah.